Okay, welcome everyone for today's quantum space-time seminar. Today we are very happy to have Joaquin from University of Washington, and he's going to tell us about random matrix universality for black holes in supergravity. Over to you, Joaquin.
Okay. Yeah, thank you very much for the invitation to speak in your in your seminars. And yes, I'm going to be talking about this work that we put out a couple of months ago with Edward Witten. And please interrupt me in any moment if you have any questions. So let me begin with some motivations, a little general, before I go into the details. So I think maybe here we all agree that from all the examples we know from string theory, we expect black holes to behave as quantum systems as seen from the outside. So one reasonable question to ask is, what properties do we expect them to have, a quantum system to have to say that it describes an emergent black hole? So here I put a list of them. First, requires a large number of strongly interacting degrees of freedom. It needs to thermalize with a particular pattern of quasi-normal modes. It has specific type of onset of quantum chaos with a very large Lyapunov exponent close to maximal. More relevant to today's talk is the fact that we expect the spectrum to have a different notion of quantum chaos that here I put late time, meaning that it's related to the random matrix universality of the level spacing statistics of the black hole microstate spectrum.
Joaquin, sorry to interrupt you so early, but just to understand the last point, do you mean both the ramp and the plateau, say, that we see in JT gravity, or did you have in mind just the plateau, just so I understand your terminology?
Yes, I mean,
here it is.
I mean both. Okay, I will say it in a couple of slides. That's part of the introduction. But yeah, I guess I mean the ramp to make the connection with only the ramp we know how to connect with gravity.
Yeah.
The plateau we also expected. Okay, so what I was going to say here is that there is this definition of quantum chaos from the 80s that whether a system has disorder or not, well, let's say it doesn't have disorder, we say that it has chaos when the statistics of the energy level looks like a random matrix. An example is the Wigner-Sormis. You write the spectrum, you order them, and then you write the histogram for the level statistics. And if it has a certain shape that is characteristic of a random matrix, then we say that it's chaotic, as opposed to Poisson statistics. Okay, and then in this paper, with a lot of authors, some of them Polchinski, Schenker, and Stanford, and others, there was this proposal that black holes behave as display also this way of quantum chaos, sharing features with random matrices. In particular, they proposed this. Well, I mean, this was already before, but they proposed to connect it with gravity to use the spectral form factor, which depends on time, and it's a product of two partition functions. And I assume you all see this before. And it looks like a two-point function where you remove the matrix element of the operators. Okay, so and this solid line is the behavior we expect from the behavior that a random matrix has, and in a model that is chaotic, this is how it will look like up to fluctuations around this solid line that I didn't draw.
Okay. When you say this is, if you are pointing on the slides, we are not able to see those points where you're pointing.
Oh, I see.
Yes. So now I can see.
Okay. 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 Maybe it has a little delay because it's okay. I'll try to keep it in mind. Okay. So ideally, we would like to reproduce this. Well, we would like the system to behave like a random matrix where up to fluctuations, it has both its ramp and plateau. But okay, first we have this slope. Well, let me go back. First, at early times, we have this slope that is controlled in gravity, is controlled by the black hole solution, and it has the feature that is exponentially in twice the entropy because we have this product of two partition functions. Then we have the ramp. And the ramp, it was shown later by Schenker and Stanford in 2018 that there is a universal solution called the double cone that always reproduces the ramp. And in particular, this can be translated into the level repulsion of the eigenvalues that I wrote down here. And there is also the plateau that arises from oscillations in level correlation. But yes, as was pointed out, I mean, we expect this to be true, but we have no gravity. We have no description in gravity that is universal. Only in JT gravity has been some results last year, but we don't have a universal picture like the double cone of. The double cone is universal in the sense, okay, it's not the topic of the talk to describe double cone, but I mean universal in the sense that if you give me the black hole, then there is a procedure that I can use to construct the double cone and construct the saddle that produces the ramp, and that's something we don't have for the plateau. But anyways, we expect, based on this evidence, that the black hole quantum system displays also this form of quantum chaos, connection with random matrices. Okay, so afterwards, Sachin and Stanford also proposed the simplest model of a black hole that captures this relationship, which is, as was already mentioned, Joaquin-Teitelbaum gravity. Let me just advert the review we wrote with Thomas Mertens about it. And the point of this model is to construct a black hole that is not only shares features of random matrices at late time, but it's exactly dual to a random matrix. So you could think of it as a toy model where you distill all the other features and focus particularly on this late time behavior. And in particular, well, as you all know, the role of wormholes is very important. So the result is that in pure JT gravity, when you compute the spectrum of a black hole and you sum over wormholes, the partition function becomes a matrix integral, a random matrix, where the random matrix is the Hamiltonian. There is a very specific probability distribution, and one can construct other models of 2D gravity, pure 2D gravity, where, okay, there's models of dilaton gravity where one can adjust this probability distribution. And okay, I guess I'm going a little fast because I assume this is known, but so this is the trace over the Hilbert space of the quantum system with this Hamiltonian, which is a random matrix. So this is a model that isolates this particular feature that we want to understand. Okay, so this is a little summary of what I think are the main points of these developments of the last years. Is that okay? The first one I already said. The relation with random matrix universality, the role of wormholes in gravity to make this happen. And finally, let me mention, and this is roughly the point of the talk, is that when we talk about random matrix universality, it's very important to identify the symmetries of the problem. And all examples that we know, at least to me, where we know what the quantum system is that is associated to a black hole, involve extended supersymmetry. And so then the point of the paper to try to understand the random matrix ensemble of a system with extended symmetry. I wrote down some examples. Yeah.
So, sorry to keep interrupting. Please excuse me. But
yeah, no problem.
Last point about supersymmetry. You can have extremal black holes in a underlying supersymmetric, say, string theory, but where the charges are such that the black hole breaks all supersymmetries. You know, they're nice black holes. And then it seems the near horizon is ADS2, etc. Yeah, go ahead.
Yeah, sorry.
No,
okay, yes.
Yeah, it seems more general than just requiring supersymmetry, but it might be probably tangential to your talk, but if you had a comment.
Yeah, I don't know if this is what you meant, but I mean, when I talk about supersymmetry, I'm not talking about looking at only supersymmetric states.
Okay.
You can look at non-supersymmetric states, and the fact that you have some underlying supersymmetry structure in the theory will affect the random matrix ensemble. Okay. So that's what I had in mind. Okay. So it's not only about the supersymmetric states.
Okay, thank you.
Sorry, but just to follow up on that, in the context of black holes, are you assuming that you're looking at a black hole whose ground state, whose lowest energy configuration is supersymmetric, or You're also allowing non-supersymmetric extremal black holes.
Yes, I was thinking about that case, the one where the ground state is supersymmetric. Yeah. So here I had some examples, and those are the ones I had in mind. And
no, but just to come back, I mean, what I had in mind was black holes where for given charges, the ground state, at least on the gravity side, is non-supersymmetric, you know? So for given charges, I mean, okay, now Shiraz's point maybe that beyond, okay, I don't know. I mean, the gravity solutions at least are all non-supersymmetric. Maybe that's already what you had in mind. I mean, these extreme black holes, you know, which you get with charges. Yeah, okay.
Yes, I think I know which ones you mean. But I'm not sure how really. I think for the random matrix classification, the fact that you have a non-supersymmetric state inside the supersymmetric theory is still important. But my answer to Shiraz was that for the rest of the talk, I'm going to focus on cases where the ground state is supersymmetric. But when you talk about the random matrix ensemble, then I think that will be the fact that the underlying theory is supersymmetric might be important also in the cases that you mentioned.
Okay. Thank you so much. Thanks, Shiraz.
So yeah. Okay. Yeah. So here you can see the examples are along the lines of also what Shiraz was saying. So first one, you have the BFSS model. There was a recent review by Magdalena. This is a model with 16 supercharges. Another example that I had in mind was the VPS black holes of compactifying type 2 string theory and Calabi-Gauss. In particular, well, there has been a lot of papers, but there was one of Sen and collaborators about writing down the quantum mechanical theory for some of these. I think they did 46. And these are models with n equals 4 quantum mechanics. And then there's also the 116 BPS black holes in IAS 5 cross S5. And well, this is just some work in progress. We're trying to write down some effective quantum mechanics that describes these excitations around this black hole. And there was also recently a paper by Benini and collaborators about similar analysis for black holes in IAS 4. Yeah, so this is the type of systems that I have in mind. Okay. So the goal of the rest of the talk will be to first define a random matrix ensemble for supersymmetric quantum mechanics. And then I will use it to define notion of quantum chaos. Okay, that's kind of automatic. And finally, I will find the black hole that is dual to this ensemble, which will be pure n equals 2 JT gravity, pure supersymmetric JT gravity, depending on how many supercharges we have. Okay. Is there any other question so far? Okay, so let me review quickly why the discussion about the symmetry is important for random matrices. So if we talk about models without symmetry, then well, we have these Dyson ensembles. And first of all, one important property we need to know is whether the system has a time reversal symmetry or not. So if it doesn't have time reversal, then we have a random Hermitian matrix. And if it has a time reversal symmetry that squares to 1 or -1, we have a different ensemble where the symmetry group is the orthogonal or the symplectic group. Here, L is the size of the matrix, or the dimension of the Hilbert space. We can also add unitary symmetries, either continuous or discrete. And in this case, the effect this has is a little less dramatic. What it does is that it tells you that the Hamiltonian is not just a random matrix, but it decomposes in blocks of statistically independent matrices for each representation of the group. So here the H1, H2, etc. will be the Hamiltonian restricted to some representation of the group G, if that's the symmetry, the unitary symmetry of the theory.
Sorry, and you have in mind, you have in mind that the rank of this unitary symmetry is held fixed as n is taken to infinity.
Of the group G. You mean
Yes, of the group G.
the
Yes.
rank of G?
Yes.
Yeah. So the G could be a U1 symmetry that the theory has, or something like that. The C2.
Yeah, but
And then we take
not UN. Right.
No.
Okay.
Yeah, sorry. Here by symmetry, I mean the symmetry of the ensemble, not the symmetry of the of the theory.
Thank you.
Mhm. So to just to illustrate the importance of identifying the right ensemble, we can look at complex SYK. So, well, you can ask me if you're not familiar with it, but it's roughly, this is the Hamiltonian. We have n fermions, psi I. They have this algebra, and they have this Hamiltonian where J's, in general, J is assumed to be random because that's how you make the problem solvable, but you can pick generic enough values of the coupling and do exact diagonalization. And then this model, for example, has a U1 symmetry. And if you look at the statistics of the energy levels of all states, then it has this distribution. So this is a Poisson-like form. So then you could see this and think that, oh, it doesn't have random matrix behavior at the times. But actually, if you look at the sector of fixed charge, so this is a histogram of the level spacing. If you look at the sector of fixed charge, then it does have the behavior on the right, which is, so the black line is the Wigner-Surmis of the GUE. Yeah. Then the dash and the blue ones are GOE or GSE. So this is just to, I mean, this is probably, this example is probably straightforward, but just to emphasize that identifying the symmetries in the ensemble is important. Okay, so now we can do the case of n equals 1. In this case, the Hilbert space, by the assumption of having n equals 1 quantum mechanics, will have a sector of the Hilbert space that will be a bosonic sector and a fermionic sector with dimensions LB and LF, and there is a -1 to the F operator that distinguish the two sectors. Another thing that this theory would have built in is a supercharged Q that is all odd and self-adjoint, and the Hamiltonian is the square of this supercharge. And in particular, well, what I said so far, it's only if the -1 to the F symmetries has no anomaly, then all this is true. Then the supercharge has this block of diagonal form where Q and Q dagger are complex matrices that are the actual random. If you want to talk about an ensemble of n equals 1 quantum mechanics, then this complex matrix is the actual random matrix in to consider. Yeah, so this model was proposed, this ensemble was proposed a long time ago by Berbashot and Sahed, and then it wasn't interpreted as n equals 1 quantum mechanics. This was done by Stanford and Witten recently in the context of JT gravity.
Sorry, Joaquin, a tangential question. Do you know context in which Berbashot and Sahed considered this?
Yeah, I think instead of thinking about many body quantum chaos, they were thinking about the eigenvalues of a Dirac operator of a single particle, and then the -1 to the F is the chirality of the Dirac operator. I think that's what
Thank you.
Yeah, I think that was the context. I'm not 100% sure, but I think that was. So the symmetry group that respects the structure we assume so far is such that this Q is in the bifundamental of ULB and ULF. And we can use these two unitary symmetries to put this Q in a canonical form in terms of eigenvalues. They're not really eigenvalues, they maybe a more proper name would be single values, but anyways, we can use these two unitaries to put in this form, and then we'll call this lambdas the spectrum of the operator. So the zeros, so if in particular the Q is an operator that maps the bosonic to fermionic sector, so it doesn't have to be, it could be a rectangular matrix, and then all these zeros represent the BPS states. And in particular, the wave function is random. So here we put in this canonical form, but when you integrate over Q and you integrate over these unitaries, the particular subspace where these BPS states live inside the Hilbert space is random.
So, sorry, I didn't understand that matrix Q. So the lambdas are not along I mean, the lambdas, it's not a square matrix, I guess, but they are along sort of row equal to column matrix. Is that right? Or
Yeah, so this, just to remind you, this Q is this part of the supercharge.
Okay. Uh-huh.
So this is a matrix where it has size LF and LB, where this is
okay.
Yeah. So the difference between the two is would be the index of the mode.
Okay, got it.
For example, yeah. Yeah. So that I call it here nu. Yeah. Okay. So okay. So then Adler and Simbauer generalize this to, well, one can use similar ideas to produce more general set of ensembles. There are 10 in total. And if you try to find what is the measure over these eigenvalues, so here we want to start with an integral over this Q, and with some matrix potential, and we want to reduce it to an integral over eigenvalues. It always takes this form, where here is have the product of the eigenvalues and the differences. The choice to make is what is this, or the information about the ensemble is what is the value of this alpha and beta. Then we have the matrix potential, of course. Alpha is, for the ensemble I was describing, is 1 plus 2 nu, and beta is 2. Yeah, so that's what it is. I'm not going to go over the derivation, but
sorry, what is nu?
Oh yeah, so nu is the difference between the index. Yeah.
I see. Thank you.
Sorry.
So you're saying that if you just write down a random ensemble of these rectangular matrices, you can show that this is the measure.
Yeah.
Okay, and the random ensemble is just integral over all elements of that matrix, unconstrained.
Yeah,
I mean, that's the initial starting measure. Yeah. Okay. Thank you.
Yes. Yeah. That's the initial starting measure, and with this free matrix potential, that part is straightforward.
I see. And in particular, if you said alpha equals, nu equals 0, so that we're back to a square matrix, we get the usual Hermitian measure. The usual.
No, because you get this lambda here. Yeah. Yes, and also, well, here we have lambda square.
Oh.
Okay, you could change variables to lambda square, but then you also have the constraint that lambda is positive. So it's not exactly the same as the Dyson one.
Okay, so then tell me, can you explain why? I thought that if the rectangular matrix became a square matrix, it would be just because it's not Hermitian.
This is a complex. This is a complex matrix. Yeah.
Okay, fine. So it's the yes.
It's this guy that is Hermitian. Yeah.
Yes. Okay, I understand. So this is the usual measure for a square complex matrix, presumably then.
Yeah.
Exactly. Okay, thank you.
Yeah, sure. Okay, so this was a little review of the n equals 1. So now I can go to n equals 2, and this is the first part of the new results in the paper. So if we have an n equals 2 quantum mechanics, we want to describe a random matrix theory appropriate for, well, having two supercharges. In particular, we can describe it this way. We have Q and Q dagger. They both square to 0. Their anti-commutator gives the Hamiltonian. The Hamiltonian commutes with Q and Q dagger. Well, if they square to 0. In particular, and for what I will say next, the fact that we have this constraint square being 0 will be important, and then will be the main important point of the rest of the discussion. Okay, we will also assume, because this happens in all the examples we have from string theory, the existence of a U1 R symmetry group generated by J, that's how I call it, and it satisfies this algebra, so it's a symmetry, so it commutes with the Hamiltonian, and it assigns a charge Q hat to the supercharge. So here I'm assuming that J has integer charges, but then the R charge of the supercharge does not have to necessarily be the fundamental charge. It could be some odd multiple of it. This wouldn't be the case if we had a non-abelian R symmetry, but because we have U1, that's okay. Yes, and the origin of the name Q hat is from the way you can realize these algebras in string theory, in SYK models. In examples from string theory, actually, the cases I know, this Q hat is 1, which is the simplest thing. Okay, and then we also have an operator that distinguishes bosons and fermions, -1 to the f being e to the I pi j. And okay, this is true unless there can be an anomaly, and I might discuss it later. But okay, let's consider Q hat equals 1. And the Hilbert space decomposes according to the arc charge. So K is the arc charge in each, and HK is the Hilbert space of the charge K.
Sorry, Joaquin, having the arc symmetry, does it make the life easier or harder?
Harder. Yeah. Yeah. It makes it easier if you want to talk about certain protected things, but when you go to the rest of the theory, it makes it harder. But it will get easier. Yeah, we'll get there. Okay, so having a supercharge of charge 1 implies that the supercharge takes this form.
In the absence of the symmetry, you just have to find a way to generate Q square equal to 0. That's if one ensures that, then you are done, right?
Yes, that's true. Oh, you're okay. I see. I didn't think about that. I didn't think about what happens if you don't have the. Yes, yeah, you only will have to do that. Okay, I would let me think about it because I.
Sure. Okay. Thank you.
Yes. Okay. So if we have this U1 symmetry, then the supercharge will separate into a sum of sectors of charge K, where the operator Qk is an operator that maps a state of charge K to charge K plus 1. And we have BPS multiplets that they come with 1 charge, and they are states that are annihilated by Q and Q dagger. And we have non-BPS multiplets of charge K and K plus 1 that are related in the obvious way. Moreover, the Hilbert space of in a fixed charge sector can be decomposed in these 3 sectors. This H naught is the BPS states. H plus are the states that participate in a multiplet KK plus 1, and H minus are the states that participate in a multiplet K minus 1K. And of course, the dimension of this sector is the sum of the 3 subsectors. And the supersymmetry algebra, in particular, this Q squared equals 0 constraint, imposes that some constraints on the dimensions of the subspaces. For example, the L plus K is equal to the L minus K plus 1, because, well, the states of charge K that participate in KK plus 1 are the same as the states of charge K plus 1 that participate in.
So H plus K and H
plus
minus, sorry, H plus K and H minus K have opposite fermion number?
No, they have the same, but they are either the fermion number. Let's say in the simplest case, K is even or odd, and that tells you whether it's a boson or a fermion. But once you tell me whether it's a boson or a fermion, then is it the so if H plus K will mean that, let's say K is even, will mean that this participates in a multiplet which is boson fermion. Well, otherwise it's fermion boson. So
okay, I didn't understand
which one is the one that is annihilated by Q or Q.
Right. I didn't understand why K being even or odd determines whether it's a boson or fermion. This one was an R. Yeah.
Yeah, that's this.
So J is the R. Oh, is the R symmetry. Okay. Yes. Thank you.
Yeah.
Yes. Thank you.
This could be anomalous, but okay, just for the simplest version of the theory, this is true.
Yeah. Thank you.
Yeah, sure. And okay, this constraint is the same as.
Sorry, I missed the definition of LK. Please excuse me. What is LK?
LK is the dimension of the Hilbert space of charge K.
Oh, okay. Thank you.
Yeah.
So
okay, and given
if you don't explicitly assume the existence of R symmetry, just having this Q square going to Q square equal to 0, would that produce a natural gradation on the Hilbert space?
No, I don't think so. Well, at least having this grading by the U1 charge is very important in almost everything I will say from now on.
So it will not
so
be
that's why
it feels a little bit like as you act with Q, you will automatically get higher and higher. Some grading, and the Q only acts in a nearby grading because Q is 0. I don't know. I mean,
yeah,
probably is not correct.
Yeah, maybe you can. Yeah, for example, you can also ask if you have. Okay, you don't have the U1, but you can ask if you have the -1 to the F or not. Then, if you have the -1 to the F, then maybe you can think about it similar to this, where you just only care about K mod, whether it's even or odd, and restrict the discussion to only that property of K. But yeah, I didn't think about that case that much because I guess from the beginning I was thinking about the cases with the R symmetry. Yeah. So yeah. Okay, yeah, so what I was going to say is that this dimension LK is a given, it's just the property of the Hilbert space. But given this LK, there can be multiple solutions for how the dimensions are distributed. But if you give me the L knots, then the solution is unique. So if you know the number of VP states for each charge, which is more than, for example, knowing the index, this is not something that is protective. If you know the number of VP states at each charge, then the solution is unique. The solution, I mean, what is the dimensions of this H plus and H minus? And this will be important because the first assumption we will make is that the number of VP states does not fluctuate. So we will do a random matrix ensemble over a fixed component of the solution of this Q square equals 0. Okay. So I will skip this, but this is just in the simplest case where we have only two charges, K minus 1 and K, then the situation is kind of straightforward. The ensemble is the same one as n equals 1, just bosons have charge, well, depending on, well, either K minus 1 or K will be boson, the other one will be fermion, and then the ensemble does not really have any difference with n equals 1. But as soon as we have three adjacent R charges, then the situation starts having the peculiar features that n equals 2 has. For example, here I call it K minus 1, K, and K plus 1. Here, K is a fixed number. There are only three charges. K is not an integer, it's just some, I don't know, 2, whatever, any number. But then the situation is less clear because we have that the supercharge is a sum of QK and QK minus 1. And Q being square implies that QK times QK minus 1 is 0. So now, in principle, we would like to say that QK and QK minus 1 are random matrices, similar to the n equals 1 ensemble. But now we have a random matrix. We have a set of random matrices, one for each charge, but they're constrained. Now, besides this, the two matrices share a common factor in the symmetry group. So before to put the QK in the canonical form, we use that is in the bifundamental of the unitaries acting on HK and HK plus 1, let's say. But these two operators have a common factor of they both either act or produce a state in the Hilbert space of charge K. So then it's not clear that we can use. Well, we cannot assume that we use that unitary independently on both Qs because they share the same Hilbert space. So the motivation was: do we need to invent a new type of random matrix ensemble, or is somehow the Adams-Bauer classification incomplete because this is not part of anything they discussed? And the answer is no. And what I want to show is that these two effects cancel each other roughly.
Is this classification?
Sorry.
What is this AZ classification?
Oh, yeah, sorry. This Aldran Simbauer classification of the possible random matrix ensembles. So there are possible symmetry groups that you SPL. There has to be 7 more. In the paper of Stanford and Witten, they model these other 7 ensembles to theories of gravity. But here the starting point of this question was that, okay, we have theories of gravity, more supersymmetry, and then what happens with the random matrix model? Is it
This is a
is
classification.
it a new
What
ensemble or
This is the classification of what exactly?
yeah? So the classification assumes that yes, it doesn't include supersymmetry. It just assumes that you have a well in the language of the application to chaos. It assumes that you have a Hamiltonian with some time reversal symmetry, and then you can have another C2 symmetry, and then there can be different algebras between that C2 symmetry and the time reversal. They classify all the non-trivial. They classify all the cases that cannot be reduced to previous cases in blocks, roughly.
Yes.
Kind of like if you have a U1, the U1 is not the different case because you have blocks of Dyson ensembles. So they classify what are the types of symmetries that would produce new ensembles that are not reducible to blocks of other ones.
Nice. Thank you.
So yeah, if it was a new ensemble, it wouldn't be inconsistent because they didn't include supersymmetry. So here, what I meant is that whether this is something new or some combination of the previous ones.
Yeah.
Okay. Okay, so actually I said this already. So this has several components. The solutions of q squared equals 0 will focus on 1. This means that the number of VP states is fixed. So we want to describe this type of ensemble. Here should be an integral. We want to integrate over this q case. We want to impose this constraint and possibly add a matrix potential. And as I said, this is what I already said. The two effects cancel each other. And what will happen is that we will have an ensemble which would consist of statistically independent supermultiplets. And that will be the result of the calculation. I think I'm doing kind of bad with time, so I'll try to. Okay, let me see. So let me give you so I'm not gonna go through the whole derivation. I will give you a simple example of how this cancellation happens between these two effects. And for that, again, we will consider a case with 3 consecutive charges, k-1, k, and k+1. And for simplicity, take the dimensions to be 1, 2, and 1. And the reason why this is enough is that when you look at the bigger case with larger values of L's, you can, to derive the measure, you can look at blocks by blocks. Well, this we explain in the paper, but so I will present it as a toy model, but this is with some clarifications is enough for the motional case. Okay. Oh yeah, and for simplicity, let's assume that we are in a range of charges where there are no BPS states. So that means this is the decomposition of the each Hilbert space. So the states of charge k-1 and k+1 are made. So okay, I think it would take me too long to read this formula, but so the Hilbert. Okay, let me try to do it. The Hilbert space of charge k-1 is made only of states in the multiplet k-1k because there is no state of charge less than k-1. The Hilbert space of charge k is made of states in the multiplet k-1k and the multiplet k+1. So that's why it has h plus and h minus. And the states of charge k+1 have only states in multiplets k+1. Okay. Then the super has these two blocks. So this is the same as the case I mentioned with 3 consecutive charges, but I chose a particular dimensions. So in this case, the canonical form we would like to make is this one where we said, so here this qk will be a row, and this qk minus 1 will be a column, two-dimensional both. And the canonical form will be to put this to 0, and the eigenvalue will be this lambda and lambda tilde. And here the two multiplets will be these blocks. So lambda and lambda tilde will be the spectrum of these two different multiplets. But of course, and to illustrate what I was trying to say before about the shared unitary group, if we integrate over fluctuations, one of it will mix these two, will not respect how we decompose this into the first state being on one multiplet and the second state being to the other. In particular, we have fluctuations that turn on this component of the matrix that I call here U. So this would be, it would rotate the way we decompose HK into plus and minus. So we need to integrate over these U and V's, and we need to make sure that it doesn't introduce any coupling between lambda and lambda tilde. If it does, then it means that the two supermultiplets are not statistically independent. So that's what we're trying to see. Are they independent? Well, the answer will be that yes. But okay, for example, in this case, the constraint is, well, this is the constraint. So we just need to multiply this matrix with this matrix. So it's lambda tilde U plus V lambda. Can do a change of variables from UV to ST. Here the details are not too important, but I just wanted to illustrate. So here, for example, the normalization is such that the Jacobian is 1, whatever the original measure was. The numerator is chosen such that the constraint involves only one of the two variables, for example, S. But then, if you look at the measure, this introduces a factor like this that couples lambda and lambda tilde. So again, to do this in detail would take me too long. So what I just want to show is that turning on these fluctuations will introduce a coupling between these two multiplets. But okay, but then we have an off-diagonal generator of this U2 that rotates, produces a unitary transformation of this two-dimensional space, HK. And what that means is that there is another measure from that unitary that contributes to the ST measure, or the UV one, however you want to call it. The calculation I'm not going to do here is to check that the measure is actually this factor. Precisely cancels the one that comes from the constraint. So here the way it works is that this delta W, what it is the well, W is, well, okay. Okay, if anyone wants to know, I can say it in more detail, but I just wanted to, otherwise it would take me too long. But
sorry, Joaquin,
yes, so the point is that
say that we don't have a very stringent time constraint here, but of course there it might be late. So you know, you can decide how you proceed.
Let me skip this from now, but yeah, let me skip this from now, and I can come back to that later if I have time. Yeah, but the point is, let me just say it in words. So when we write something like, when we write the multiplet in this form, we already assume a canonical way to decompose HK into H plus and H minus. That decomposition is not something fixed a priori. You have to, in principle, that's random, which states correspond to plus or minus. And the fact that when you integrate over these matrices that you need to, that the composition is not fixed, also affects the measure by a factor of lambda square plus lambda tilde square, and that measure exactly cancels a similar factor that appears in the constraint. That's the point of this example. And okay, organizing the calculation appropriately, as I said before, the most general case reduces to this one. But there is only one exception that I can mention, which is that sometimes the constraint can be redundant, and this leads to divergences. For example, if you take 4 consecutive charges with all Lk equals 1, then the supercharge will have this form. So that I call, so each of the qk's will be numbers, will be these 3 numbers, and I chose to call them lambda u and lambda tilde. And if you try to write down the constraint that q square is 0, then we will have 2 constraints, one that lambda times u is 0 and u times lambda tilde is 0. But both constraints tell you that u is 0. So then if you so if you try to integrate over u, then that will produce a delta function of 0, so that will be infinite. And in particular, we would like to, well, here what I draw with the blocks is we would like to be able to fix this u to 0, so that we can talk about these 2 multiplets independently. But then we would like the measure to be finite, and this seems to give infinite. And another thing we show in the paper is that you can derive a finite measure by using something similar to the Faddeev-Popov procedure, where you write the delta functions as integrals, and then there is a symmetry of this integral, and it can be fixed in the same way as Faddeev-Popov do. And okay, then that produces a measure that is unambiguous. But again, the result ends up being that this delta function is just 1, or it's something independent of lambda and lambda tilde. Okay. Okay, so the final result that again, I didn't give you all the details because I hope to say some words about gravity as well, is that all the non-BPS states of charge k and k plus 1 are all the multiplets are statistically independent of each other. That means that the overall measure over all these eigenvalues is a product of individual measures on each supermultiplet. So here what I wrote is the same measure as n equals 1 theory, as this Alderson-Bauer measure. And here lambda there will be one of these lambda i's for each of the supermultiplets. Another result of the analysis is that the value of alpha and beta. So beta is always 2, and alpha will be 1 plus the number of BPS states that share the same charges as the multiplet. So if the multiplet has charge k plus 1, then both BPS states of charge k and k plus 1 will contribute to this value of alpha. And that appears because some of these matrices are these blocks of the supercharge are rectangular. And finally, the BPS states of R charge k inside the Hilbert space of charge k, they span a random subspace, and they have random wave functions. And this would be different than say, so I mean, this is what we derive from the motion integral over the supercharge. But this would be different than, for example, I don't know, something one could do that would be wrong would be to say that the BPS states are kind of frozen in the Hilbert space, and then the randomness is in the non-BPS states, and then something like that. I don't know. If you try to do the ensemble over the whole theory, the whole supercharge, then it also tells you what happens with the BPS states. And this connects with a proposal of this paper of Lin, Maldacena, Rosenberg, and Shan, which propose a notion of chaos of BPS states by computing late time correlators and what the late time correlators are doing is computing matrix elements of operators between the BPS states. And well, the notion of chaos is that when you average over these BPS states is that those BPS states are they have a complicated wave function inside the Hilbert space. They phrase it in a different way, so it's not completely straightforward to connect it with their analysis, but I'm pretty sure they are the same. Okay. Let me see. Okay. Is there any question about this result? Okay. Okay, let me skip this a little bit. So here I just make some comments about the general case. We can restore Q hat. Then the multiples will have charge Q and Q plus Q hat. Sorry, K plus Q hat. We also assume that charges are integers. We can consider adding background charges. From the gravity side, this comes as adding theta angles. Yeah.
One question. So here you fixed the dimensions of various dimensions of Hilbert spaces of the given charge, right?
Yes.
As opposed to fixing just the overall dimension.
Well, the fixing.
Isn't that you wanted to do that?
Let me see. Okay, I don't know where I have it. So the LKs, these LKs are fixed before you even say what the Hamiltonian is. So before you even, that's a property of the Hilbert space. For example, in SYK, it just the Hilbert space of each charge, you can make the Hilbert space by starting with the vacuum and acting with the creation operator of these fermions. And then the dimension is just the number of states you can make with a certain number of fermions, for example. So it's something you can compute without even talking about the Hamiltonian or the supercharge. The part that depends on the dynamics is how is this distributed into the L plus, L minus, and L zero. So that involves the dynamics. And what I'm saying is that if you fix L zero, so if you assume that our ensemble does not average over L zero, and the reason I'm doing it is because that seems to be what happens in gravity. Then if the L zero is also fixed, then L plus and L minus will be determined through this through the constraint of Q square being zero.
Sorry, maybe you said this, but gravity, why is it that the L0 is fixed?
Yeah, so okay, that would, yeah, let me come back to that later. I will talk about it in a couple of minutes. Yeah.
Okay.
Yeah, but what happens is that when you compute any quantity that would give you the variance of this L0, it just happens to vanish. Yeah. Well, I mean, there are several things that could have happened. First, when you compute the variance of the index, that vanishes. So the index is not affected by this factorization puzzle. So that means that we could also consider ensembles where even the index is different. That you don't have to do. Then it takes a little bit more work to show that these wormholes also don't affect the number of VPS states. And then not only you fix the index in the ensemble, but you also fix the number of VPS states. And then I will explain in a couple of slides, hopefully, how that happens in gravity.
Okay, thank you.
Yeah, sure. So yeah, and once we fix L0, then all these other dimensions are fixed. Yeah. Yeah. Okay, let me skip this. So, well, I just had some pictures here of just to show about this SYK. So you can do it in n equals 2 SYK. You can construct what these eigenvalues are of each supermultiplet, and then you can look at their spacing distribution, and then you can see that they follow the pattern that they should, based on these random metrics. Well, yeah, okay. Let me just leave it at that. Yeah, I want to move on to gravity. Okay, so in the rest of the talk, I will describe this n equals 2 JT gravity and how it reproduces these features of the random matrix ensemble that we derive. Okay, in particular, n equals 2 JT gravity is relevant because it's the one that describes excitations of the throat of these 116 BPS black holes in ADS 5. So that's another motivation to be interested in this theory. Well, of course, when you couple it to matter. And here I will describe pure JT gravity, which is dual to the ensemble on the nose. If you couple it to matter and you put all the things that come with string theory, then it will be dual to some specific Hamiltonian, of course. Okay, so n equals to JT gravity, up to boundary terms, the action is the sum of a topological term proportional to the parameter S naught. I will assume you all heard talks about JT gravity, but if you have any question, let me know. So this is the first term, so whenever you have a wormhole or anything that adds topology, it changes how it scales with S naught. It also has a topological BF theory term with supergroup SU1,1/1. So this is a superconformal group that has SL2R and U1 as bosonic generators, and it also has 4 fermionic generators. So we will study this in spaces with asymptotically ADS2 boundaries with a fixed length beta, and fermions are twisted by e to the I alpha j. The boundary conditions break the superconformal symmetry, and the dual theory doesn't have any. The only symmetry it has is the n equals to quantum mechanics that I used before. Yes, and this alpha parameter here is interpreted as a chemical potential, or well, imaginary chemical potential. And beta is the inverse temperature, of course. So whenever we compute the gravitational path integral with these boundaries, we are
why are you twisting with the this twist computes? Is that computing the index or the partition function, or neither?
Oh no, sorry. By twist, I meant just that the fermions get a phase as you go around the thermal circle. So there is like turning on a chemical potential that is arbitrary.
So a chemical potential coupling to the U1 R symmetry?
Yes.
Okay, so
yeah, J is the U1. Yes, this J that was the U1 before is the U1, is a gauge field here that comes from this sector of JT gravity. Yeah.
Right. So this is the thing you would want to do if you were computing trace, a partition function with a chemical potential weighted. Waiting this, yes. Is this commuting with the supercharge or not? I mean, this is not commuting with the supercharge, right? This is not.
No. So this is not protected yet.
Yeah. Okay, fine. Okay, thank you.
Yeah. Only for a particular value of alpha. Okay, so this is the standard thing people do in JT gravity, just n equals 2. So we have a gauge field, we have fermions. Yeah. So now we have this observable to compute for each boundary. Yeah. So the partition function, let me just tell you what the result is. I don't know how familiar people are with it, but if you're not, I can tell you more about it. But well, it has several features. First, it has an overall factor of. Oh, sorry, I shouldn't say it. This is the partition function in the disk. So I didn't add any wormhole yet. This is just the Euclidean black hole. So I want to compute literally the trace of e to the minus beta h, e to the I alpha j. Okay, so the first term is topological. It's this e to the s naught because it has the topology of the disk. It has a sum over an integer n. This is a sum over saddles. If charges are integers, then alpha is identified with alpha plus 2 pi. And that means that there is no way to distinguish alpha from alpha plus any multiple of 2 pi. In the boundary, this is kind of straightforward, but in the bulk, they appear as different saddles. If you try to write the saddle, then the saddle will depend on the real value of alpha, and then you have to sum over shift of alpha to recover the integrality of charge. This happens also, for example, in Reiser-Nordstrom. If the boundary condition with chemical potential mu, even if charges are integer, the solution depends on mu as a real number. And if you shift mu by 2 pi over beta times an integer, then you produce different gravity configurations that after you sum over them, you recover an integer charge spectrum. Okay, so this exponential is the classical action. This is the first term in the. Yeah.
Sorry, just to make sure I'm understanding this. Are you saying the following, that if you turn on an imaginary chemical potential and charges are integers, then clearly the partition function has to be periodic in the chemical potential with periodicity, let's say 2 pi.
Yeah.
But any particular gravity solution does not have this feature. It's like it's a multi-sheeted kind of thing. But when you sum over all of them, you recover the periodicity.
Yeah, that's what I'm saying. Yeah.
Okay, thank you.
So somehow the details of the gravity solution care about the real value of alpha, so you have to sum over them, and sorry, I think my headphones are out of battery. Okay. Can you hear me?
Yeah. Yes.
Can you hear us, Joaquin?
We can't hear you.
Is it because it's using some?
Yeah.
Hello?
Oh, yeah.
We can hear you now.
Okay, great. Okay. Yeah, sorry, my headphones are out of battery. Okay, that's fine. Okay, so so then we have this term is an exponential, and this is just the classical action. The first term, sorry, I noticed it's a little small. The first term is from JT gravity, is the standard one, and the second term comes from the gauge field, and you can see it's proportional to the chemical potential squared. It comes from the gauge field action. And this is a one-loop determinant from the fermions. Well, it also gets contributions from the gravity mode and the gauge field. But most of the interesting chemical potential dependence comes from the fermions, from the gravitinos. And finally, one can also add a theta angle term in the bulk, but let me ignore it for now. This is related with this background charge that I mentioned before that one can add. But okay, the spectrum can be extracted by rewriting this as a sum over charges instead of sum over cells, and it's just a more complicated version of a Poisson resummation. So we have two terms. The first are the VP states. So we see it's a sum over k. K will be charges, and there is no beta dependence, so they're all states of zero energy. And what this formula is telling me, so this goes as e to the I alpha k, and this quantity here is the number of VP states of charge k, predicted from the disk. And then the second term is the non-VP spectrum, so it has a sum over charges, and now the chemical potential dependence is e to the I alpha k plus e to the I alpha k plus q hat, and this is the contribution of the two states of a multiplet, super multiplet. And then the rest is the density of states of the super multiplet. And you see it looks very similar to JT gravity. It has a sinh. It has a factor of E in the denominator that comes from the fermions, roughly. And it also has a gap E naught that depends on the charge. So each super multiplet might have a VP state or not, depending on the ratio of charges. So this cosine only applies for charges smaller than q hat over 2. If q hat would be 1, then the VP states would only be there for 0 R charge, for example. So for some values of the R charge, there is a VP states, and then there is a continuum of non-VP states that start with a given gap, with a gap given by this function E naught that is just quadratic. So the spectrum looks like this. So if you are in a good charge sector with the VP states, then it will look like this. And if you are in an arbitrary sector that doesn't have any VPS states, then it will look, well, the same, but without the large number of ground states. And okay, this behavior is universal for black holes with IDS 2 throats. That's kind of the topic of a different talk. Okay, and what this tells us is, if our ensemble is correct, it tells us what the spectral curve is, or what is the matrix potential. So we can read off that function f of q dagger q from this density of states. Sorry, that from the continuum part. And then from the number of VPS states, well, we read off what these L knots are. So this is the number of VPS states for charge K. So this is what in the first part of the talk I call L naught K. So we can read it off from here. And the continuum part again is the spectral curve that is related to the matrix potential in the large shell limit. Yeah, so something new about this model is that the number of VPS states also grows with L. So the number of VPS states is of order e to ds naught, just like the continuum part. Sorry, maybe I didn't write it in this page, but you can see it in here. Both the non-VPS and the VPS part, they all grow with e to ds naught. So having a number of, or having rectangular matrices where the difference between the two sides grows with L, this is something that didn't appear before in the studies of JT gravity, and it's sometimes called Penner models, and it's similar to adding logarithmic terms to the matrix potential. Because if you remember, the way that VPS states affect the measure is by changing the power of lambda in the overall. So it was roughly, the measure was d lambda over alpha, and then there is a e to the minus L f of lambda. So then what I'm saying here is that this parameter alpha can also be proportional to L, and then that can be absorbed in a logarithmic correction to the matrix potential. And this is important. We prove that this doesn't affect much, but in principle it's important because this can change the way you derive the loop equations, whether this parameter scales with L or not. So something we show is that other than some small features, for example, the fact that the spectral curve has a pole at the origin, okay, I can tell you more details, but other than small features like this, this logarithmic term in the matrix potential doesn't affect the loop equations. So this is important to match in with.
Sorry,
matrix.
But you said that in the case of all gravity examples, q hat was 1. Is that right?
In the case, no, what I meant is in the case of, I meant in the case from, like, for example, in string theory, this 116 BPS black hole, if you look at what is the theory of JT gravity, then Q hat is 1.
Yes.
Or in the cases of ADS4.
Yes. So in all those cases, this complication does not arise.
No, I think this is unrelated. Here, Q hat can be whatever. Here, what I'm talking about is the fact that so before, when I talk about n equals 1, I mentioned that there is this parameter alpha that appears in the measure. And that parameter is 1 plus the number of VPS states.
I see. I see. So even when there are no VPS states, you have.
Yes, then that alpha is 1. And
okay,
what I'm saying is that in all the cases that people studied before, this alpha is a fixed number when you take the large L limit. This is a statement about the random matrix model. And now what happens here is that this parameter alpha also scales with L because the number of VPS states is proportional to e to ds naught.
I see. Sorry, no. When Q hat is 1, you have BPS states only at charge 0. Is this right?
Yeah.
That does not simplify anything?
No, because you still have this. Well, it simplifies in the sense that you only have. Yeah, you only have this. This only happens for k equals 0, but
Okay, thank you.
Maybe it affects the values of K's that are relevant for this point.
Yeah, okay, thank you.
Yeah, sure. Thank you. Yeah, okay. We continue. So okay, now I can talk about the two-sided wormhole. So far I discussed the disk. So this doesn't prove anything so far. It's just it's a way of extracting the matrix potential, but it doesn't really test much about the duality with the random matrix. Well, okay. Sorry, let me go back. There is one thing that is consistent with, and it's the fact that this behavior, whenever the density of states goes to 0, it always has a square root. That's a feature of a generic random matrix model. So if it was a different power, or I don't know, if we had a different behavior, that might be inconsistent. But other than that, this doesn't show much. So now we can look at the two-sided wormhole. So here we have the gravitational path integral with two ADS2 boundaries with their own beta1 alpha1 and beta2 alpha2. Now alpha1 and alpha2 are the two chemical potentials. So maybe you can look at this here. So we want to compute the connected contribution to this generalization of the spectral form factor when you add this chemical potential, the U1 symmetry. Okay, so the random matrix ensemble features that we want to reproduce by gravity is first, no fluctuation of the number of BPS states. So we stay in the same component of Q squared. We also want that supermultiplets are statistically independent. And what this means is that if we restrict the trace to a single supermultiplet of charge, when I put K1, I mean K1 plus Q hat. So when we restrict the trace to a supermultiplet K1 and a supermultiplet K2, that this quantity is non-vanishing only when we look at the same supermultiplet. So this is what's telling us that the supermultiplets are statistically independent. Finally, within a given supermultiplet, or the prefactor that multiplies this Kronecker delta, should match the universal double scale random matrix answer that one always has. So it's a very specific function of beta1 and beta2. So we should reproduce all these things from gravity. So to do the calculation in gravity, we can do the usual trick of SSS of we take this leading order wormhole and we cut it in half. And now we do the path integral on the two halves, which are called trumpets. And now the interior circle depend on the geodesic length p, but also depend on the U1 holonomy phi. So we have these 2 degrees of freedom in the internal circle. We need to when we glue the two halves, we need to integrate over both the internal U1 holonomy and the internal length. Yes, and again, well, this is hopefully familiar to all of you. So when you integrate out the dilaton and the dilatino in JT gravity, you restrict to hyperbolic surfaces. So then once you fix these internal parameters, then the integral over each of these halves comes only from the boundary mode, which is the generalization of the Schwarzschild mode. Okay. So again, but here I'm just quoting the result, but the trumpet path integral can be computed using the Schwarzschild mode, and you see it has a similar structure. It's a sum over saddles related to the charge integrality. It can have a theta angle term or not. This is a one loop fermion determinant, and this is the action, classical action. And this can be Poisson resounding to a sum of charges. So the first feature we see is that we get no contribution from BPS states. This is related to a question that was asked before. So that when you sum over charges, all states come in these pairs, and they all come with a gap of E naught. So all the contribution comes from the non-BPS sector. This is actually not completely trivial. Okay, just for a comment, it could happen that when you integrate over the internal geodesics, that the beta dependence could cancel this exponential from the gap. But we can show, well, we show in the paper with Witten that this doesn't happen. So there really is no fluctuation from the VPS states to any order in the large S0 limit. And the thing that it's easier to see that we pointed out in this paper is the fact that if you pick the value of alpha that corresponds to the index, then all the contributions from wormholes vanish because this factor here vanishes. Because the value of alpha that corresponds to the index is precisely the one such that whenever you have a contribution from a supermultiplet, it vanishes. Yeah. And we also give a more general explanation that we expect should be true for any black hole, which comes from the presence of a fermion zero mode. So the fact that the index factorizes is a robust statement, but the fact that the VPS states number fluctuate or not, that's more non-trivial, and that we can only show for pure JT gravity. Okay, and another, okay, let me skip the second comment, but another feature is that the different supermultiplet have the same gas as the disk. So this inode that appear here didn't necessarily have to be the same as the same function of k that appeared from the disk, but it is. And that's important for the result to make sense. And finally, this function of the internal length and the inverse temperature is exactly the same as bosonic JT gravity. So this is also important. So all these little features are important.
A quick question, Joaquin. Is this feature also true for higher moments? The fact that the second moment of the index does not have any non-trivial constant?
Yeah. So the reason it happens is that for JT gravity, whatever number of boundaries you have, I don't know, let's say something like this, and you can have any topology. Sorry, maybe I didn't draw it very well, but you will always be able to cut it by trumpets.
Okay.
So then when you glue the internal wormhole complicated part to the trumpet will always be just exactly zero when you evaluate it for the yes, and this has a reason that is more general than the JT example, which is from, well, there is a fermion zero mode that is guaranteed by supersymmetry. That it doesn't affect the disk, so the index in the disk can be non-zero, but it affects the geometry with wormholes.
Thank you.
Yeah, sure. Okay, let me skip this. So now that I told you what the trumpet is, you can put it all together and compute the whole amplitude of the wormhole between the two boundaries. So here I integrated over the internal U1 holonomy phi and length b. I multiply two trumpets together. What happens is one important feature first is that when we integrate over the U1 holonomy, if you look at the dependence with the U1 holonomy, it's this. So when we have the sum over the two charges on the boundary 1 and boundary 2, the integral over the internal holonomy imposes that the supermultiplet propagating on the two boundaries is the same. So this produces the sum over a single k. So the contribution from the supermultiplet on the two boundaries correlated, and it produces this Kronecker delta that I was mentioning before. So the integral over this internal holonomy somehow ends up always imposing the fact that the multiplets are statistically independent. Okay, and then the function of beta, the overall one here, is exactly the same as in bosonic JT gravity. And it actually is universal for any value for any of the Atlas invariant ensembles. So the fact that the trumpet kind of magically produces this simple answer here was important for making that work. Okay. Okay, let me skip this. Okay, and then let me just make some comments about the three-sided wormhole so we can go over to the next case with three boundaries. And now we can ask if we extract the contribution from individual multiplets K1, K2, and K3, then does the answer have support only when the three multiplets are the same? And moreover, is the prefactor precisely what you would predict from the matrix model loop equations of the corresponding to the matrix potential predicted by the disk? And Okay, the answer is yes. I'm not gonna go over the calculation. Yeah, unfortunately, I feel like I don't know. Probably, yeah. Probably each of these little calculations could take a whole hour. So it's I don't know. Had to decide whether to focus on that for a whole hour. Try to tell you a little bit more of all the results. But okay, you can compute so the previous picture was like this. So when you cut by trumpets, we need the partition function of shady gravity in the three-hole sphere. This is what this formula is telling us. So we have three trumpets glued together to this quantity, which is the path integral of the sphere with, well, genus 0 and three boundaries. And it depends on the three geodesic length and the three one-hole enemies. So in JD gravity, this is given by Val-Peterson volume. Now, unfortunately, part of the paper, that's also a reason why it was a little bit longer than expected, is that this wasn't studied for n equals 2 surfaces in the math literature. So, okay, we had to compute it from first principles, and we got this for the. And okay, let me just tell you that if you take this and you plug it into the formula gluing with the trumpets, then you get an answer consistent with both the statistically independent of the multiplets and a function consistent with the loop equations. And okay, that's what I wrote.
That volume is independent of B1, B2, B3, is it?
Oops, sorry.
Is it just once, because
well, that's just because it's the simplest case of the three-hole sphere. Yeah, so in the case of bosonic JT, if we had the three-hole sphere with B1, B2, and B3, the volume would be just one, because given the three boundary length, there is only one pair of pans with a hyperbolic metric there's only one hyperbolic metric with a given boundary length. Now, what happens in n equals 2 is that, okay, let me say what happens in n equals 1 first. You also have fermionic moduli in the moduli space of hyperbolic surfaces. And if you read the paper of Stanford and Witten, all the wormholes with genus 0, they all give 0 because of the fermion 0 modes. What happens here is that you have the fermion 0 modes, but besides you also have a constraint that the three U1 holonomies have to add up to 0. And that's to make sure that the U1 gauge field is smooth. But the constraint that the sum of the three holonomies is 0 gets fermionic corrections. So it's 0 up to fermionic terms. And then this second derivative here of the delta function arises because this is how many derivatives you have to take to pick as many fermionic terms as fermionic coordinates are being integrated, roughly. So you get a non-zero answer. So the answer is similar to the bosonic one up to this. So the important thing here is that the prefactor is not too important, but the important thing is that we have two derivatives. Oh, sorry, here I meant one if you have bosonic JT. For example, if you have bosonic JT with bosonic U1 gauge field, you get just the delta function of phi1 plus phi2 plus phi3. Yeah. So this is very similar up to the derivatives.
Sorry, Joaquin, maybe you said this, but
Yeah.
what calculation on the gravity side fixes the alpha and beta parameters of your matrix model?
No, nothing does it. I mean, you have, so here I show some example, and you need to compute all the higher genus correction.
Okay.
And then they have to match with the loop equations for some value of alpha and beta.
Okay.
And then hopefully the value that you would predict based on the symmetry is the same as the value you get from gravity.
Okay.
So there are a lot of things that have to conspire to work. So it's kind of similar to the original SSS paper, but there are way more moving parts that they all have to match in some non-trivial way. Yeah. So the value of alpha beta is from gravity is not something you fix. It should come from the higher genus. Okay, so this is the last slide, I think. Besides, yeah. So I should finish soon. Sorry, it took me a little longer. So okay, I already predicted that I would run out of time, so I didn't try to show you the details. But in the paper with Witten, we studied the path integral of n equals 2 JT gravity on surfaces with any number of wormholes and boundaries. So this required deriving some new math results, as I said before. So first, we want to do the gravitational path integral, and we need to derive from the original path integral the measure over the modular space of n equals 2 Riemann surfaces, or the Weil-Petersson measure. So this Weil-Petersson measure was not derived for n equals 2 surfaces, so we had to do that. Then we use this and other results to derive the topological recursion similar to Mirzakhani. So this is something else that was not done for n equals 2. It was done for n equals 1 before JT gravity, but it wasn't done for n equals 2. And then finally, we derived this topological recursion, which looks like a more complicated version of Mirzakhani's ones. And then we were able to show that it precisely matches with the loop equations of the matrix model. So all this I'm not gonna even try to describe, but if you are familiar with SSS, you might roughly see how this works. Although let me say that n equals 2 case had a lot of interesting features that don't appear in any previous example, so it was kind of interesting to do it. Okay, so but the conclusion of this analysis is that to all orders in the e to the minus s expansion, the n equals 2 pure JT gravity black hole is dual to the precisely the n equals 2 random matrix model that we proposed in the first part of the talk. So that's the result. Okay, just some comments. We also studied the cases with time reversal, so you can combine supersymmetry with time reversal. In this case, we studied two cases. So if you have a time reversal symmetry, I think the standard convention in particle theory is to call it T if it commutes with the charges, and CT if it anti-commutes. So then we analyze what happens if you have a T symmetry or a CT symmetry. And here I wrote some words about the type of ensembles. So basically, you produce different versions of the different combinations of the Altran-Zimbabwe ensembles for each supermultiplet. And we also show, at least in some examples, that all these extensions with time reversal symmetry have a gravity dual that includes unorientable surfaces. So then we had to compute the path integral of JT gravity with cross caps and things like that. Yes, and that's it. Yeah, perhaps the only case we didn't study that would be interesting is what happens if we have another unitary symmetry that commutes with the supercharge, but it's not the R symmetry. Things like that, so it can be made more complicated, and those cases are definitely important for the string theory examples that I mentioned in the beginning. For example, in the 116 BPS case, there are a lot of chemical potentials one can turn on of symmetries that commute with the supercharge that this analysis doesn't incorporate. But presumably, hopefully that part is easy to add. Okay, so just say some conclusions. So we derive the n equals 2 random matrix ensemble, and therefore can be used to define a notion of quantum chaos for strongly interacting supersymmetric systems. And we also derive some similar results for n equals 4, but very preliminary. Actually, for n equals 4, just to mention it, is considerably, extremely more complicated. The structure of the constraints is way more complicated than just saying that Q squared is 0, and there are constraints that are redundant and constraints that are not independent from each other. So we were only able to do very, very little on this on n equals 4. This would be the case relevant for the BPS, have BPS black holes in flat space 4D. Okay, and the second part, I studied pure JT gravity and give a model that is exactly dual to this ensemble. As a hope, I would really like to use this to perhaps in some I would really like to use this to understand better the examples from string theory and where this chaos and these wormholes come from. And I felt like at least the examples that are best known will require understanding this generalization of random matrix universality. And finally, well, what I mentioned, the VPS states are not independent from the non-VPS sector. They all come from the same rectangular matrix, and there is a prediction about the statistics of the wave function of the VPS states. This is not visible in pure gravity, but it can be visible in correlation functions. And I think this is something that would be interesting to analyze further, especially in the string theory models. Okay, sorry for the extending me. Thank you for your attention. Yeah.
Thank you very much, Joaquin, for a wonderful talk. Let's see if there are more questions. First from Zoom audience.
Okay, I had a quick question, please. In the case of the n=4 Yang-Mills black holes, when the R symmetry here that you have here, for which you were turning on a chemical potential, that's some linear combination of the Cartan charges of n=4. Is this correct?
Yeah. Maybe also with the angular momentum, but yes, it's some combination. Yeah.
Yes. So the fact that, and you said that in that case you had Q=1.
Yeah.
So and so we're finding no BPS states except exactly at the charge that you put in. So is the fact that is this fact a prediction that there are no BPS states away from this 4-parameter manifold of black holes?
Yes, I think it's a prediction. Yes. It's a prediction of. Okay, let me say it for the case of n=4 GT gravity, because in that case it's a little more easy to state. If you have BPS black holes in flat space from compactifying type 2 and a Calabi-Yau, let's say, then they have an ADS2 throat with an emergent n=4 JT mode. This is the analog of in that case the air symmetry is SU2, and what happens is that the VPS states come only with J=0. So they only have which there has been multiple arguments for that before, from maybe Shoksen, maybe Sandeep Trivedi as well, and other people. Yeah, so in principle you compute the index, but in principle you don't know whether you have the VPS states that have charge 0 or they could have multiple charges. But they happen to have the minimal one that you need, in a sense, the minimal one to reproduce the index and nothing else. Because if you have a generic theory, you could imagine that if you have anything else, it could, it wouldn't be protected to becoming a non-BPS multiple or something like that. Yeah, so in the case of the ADS5 black hole that you mentioned, the R charge I'm talking about is a combination of the Cartans and angular momentum plus a shift. So the origin of what we call zero charge is not. Well, I guess you have to say what you mean by charge. But what we call zero charge, it corresponds to the charge that satisfies this nonlinear constraint in the black hole.
Yes.
So what we're saying is that there is only one charge that gets the most of this of the VPS states, which you cannot see in the index, right? Because in the index you have to sum over.
Yeah. But you are saying that there are states only on this nonlinear constraint that are moving away, and there are no BPS states.
Yeah.
I see.
But the nonlinear constraint can have corrections, right? Because that's a classical statement.
That's fine. But you're saying that there's a codimension one surface in the space of charges on which there are BPS states, and away from that there are none.
Yeah, at least to leading order. I mean, there could be. That's why I was saying that we cannot show in general that higher order terms that do not contribute to fluctuations in the number of VPS states, for example.
And sorry, this thing takes into account JT gravity. Is it totally clear that the other fields of supergravity are somehow not important?
Yeah, so if in JT gravity, yeah, so what happens, so well, there are two, okay, here I was talking about very small corrections of order e to the minus s naught for pure n equals to JT gravity. That, of course, is beyond anything we can say in the higher dimensional picture. In the higher dimensional picture, what you can say is that, okay, if the theory in the throat is JT gravity coupled to matter in some very specific way, then in some regime, there's some answers, some quantum effects that are universal and come only from the JT gravity mode and are not affected by matter, by correction from matter. So that's why I don't want to make it sound like it's an exact statement for the type black hole.
You know, I say because there's some evidence that there are additional supersymmetric black holes which involve condensation of charge scalars. I'm talking about these papers by Santos and friends, which suggests that there are supersymmetric states away from your manifold, and suggests that the charge scalars are important for seeing this.
Yeah. So that for sure would not be
captured by what you have, right?
Would not be captured by this. Yeah.
Okay.
From gravity, that's obvious because the JT analysis is
you just don't have that mode, right? You just keep it to zero, right?
The JT would. Yeah, JT is just a way of computing quantum corrections around a given black hole, and it's just a universal feature about the temperature dependence of and in this case, the chemical potential dependence of the quantum corrections in a certain regime.
Okay.
So if you're starting from a different metric, then if your background is different, okay, that will count as perhaps a.
No. I was thinking that fluctuations would lead you to a different metric. You start on your manifold, on this 4-parameter manifold. That there your description is correct. But if you take into account the correctly the fluctuations of modes that would take you away, if you had slightly different charges. I was thinking you should see that when you take into account the appropriate fluctuations of modes.
I see. Yeah, I'm not sure if you can see that from JT gravity.
Yeah, I suspect you need to. Anyway, thank you. Yeah, thank you.
Yeah, the way I was thinking about it is that probably they will appear as completely different saddles that you need to include. That it's not obvious that they are even connected to each other.
It's possible, but anyway, thank you. Yeah.
Okay.
From here. Well, we have had quite a few questions during the talk, and it must be quite late there. Okay, thank you again for one talk.
Yeah, thank you very much for the invitation. Yeah.